Hello everyone. Welcome to the course Principles and Applications of Mechatronic Systems. I'm your instructor, Jiamsheng Jia. Today we'll study Chapter 2, Fundamentals of Automatic Control, Application of Automatic Control Systems 1. Automatic control systems are widely integrated into various fields of modern society, driving technological advancement and industrial upgrades. So what role do they play in practical applications? Let's delve into their practical functions and effective application methods. 1. Control system compensation. When the original system's performance fails to meet standards, compensation measures must be taken. System compensation refers to adding devices or components to change the system's structural characteristics. Based on the position of compensation devices, there are several types. A key focus is analyzing the PID control rules in series compensation using MATLAB. 1. Series compensation. The compensation device GCS is connected in series within the forward path of a system's inherent section. 2. Feedback compensation. The compensation device GCS is connected in the feedback loop with the section requiring compensation, forming a local feedback loop. 3. Composite compensation. On the basis of feedback control, input compensation is introduced, which can be classified as setpoint input signal compensation and disturbance input signal compensation. 4. First and second order time domain analysis and conclusions. A servo system with a proportional coefficient Kc equals 0.5 in series compensation is analyzed. Comparing the step response curves, post-compensation shows improved stability and reduced overshoot, but worsens steady-state accuracy and halved gain. 5. Proportional integral control. 1. Action rules of PI control. Time domain expression and transfer function of PI control are presented. The P term plays a dominant role, and the I term plays a supporting role. Combining their advantages, P responds quickly to disturbances. I eliminates steady-state error. 2. Characteristics. 0. Steady-state error control. Introduction of the I term reduces system stability, so a larger proportional gain of the PI controller is required. Continuous integration occurs when deviation exists, which may cause integral saturation in objects with large lag. PI control is suitable for systems with pure lag, small time constants, and no allowable steady-state error. 3. Proportional derivative control. P dominates, D assists. It belongs to differential control. It enhances stability, but has poor anti-disturbance capability. Suitable for processes with stable parameters. Improves control quality when facing large load variations. 4. Proportional integral derivative control. Expressions and transfer functions, both ideal and practical PID output expressions and transfer functions are provided. 5. Characteristics and applicable scenarios. Combines the advantages of PI and PD control, strong anti-disturbance ability, and improved stability. Applicable to processes with large capacity lag, moderate pure lag, and no tolerance for steady-state error, such as most temperature and composition control systems. Comparison of responses under different control rules. PID performs best, followed by PI, then PD, with deviation, then P, and I is the least effective. 6. Control systems Simulink-assisted design and analysis. Using a control system transfer function as an example, Simulink is employed to analyze dynamic responses under different control methods, displaying the Simulink block diagrams of P, PI, PD, and PID control systems. 2. Single-loop control systems. A single-loop control system is a closed-loop system comprising a measurement transmitter, controller, actuator, and controlled object. It accounts for over 80% of applications in industrial production and forms the foundation for other control systems. Mastering its concepts is essential to control technology. System analysis includes its composition and performance indicators, among other aspects. It consists of a set point and is affected by disturbances. During design and application, both control strategy design and regulator parameter tuning are critical. Missing either would hinder control quality and optimal system performance. 1. Measurement and transmission stage. The diagram shows various temperature measurement and transmission devices: pressure thermometers, electric contact thermometers, temperature sensing elements, integrated temperature transmitters, semiconductor thermometers, etc. Performance and function. Performance involves the transfer function. The function is to convert industrial process parameters into standard signals. Basic requirements: accuracy, speed, and reliability. Measurement transmitter working characteristics include range, 0 point, input-output relationship, span adjustment, and zero shift. These are the input-output characteristics required to meet measurement and system operation needs. 2. Actuator stage. The actuator is at the terminal of the control loop and is the final control element. Its performance and selection are closely related to control system performance indicators. It is crucial to select appropriately under special working conditions. The most common actuator is the control valve, composed of the actuator and the regulating mechanism. The diagram shows various types of actuators, including pneumatic diaphragm, pneumatic piston, double-acting, long stroke, electric, and electrohydraulic actuators. 3. Control algorithms of controllers. Analog PID algorithms. Traditional analog instruments implement PI, PD, and PID algorithms using hardware. Digital PID algorithms, implemented via software in computer-based control devices, include position, incremental, and velocity algorithms. On and off control algorithms include two-position, three-position, and time-proportional control algorithms. The diagram shows types of controllers: analog controllers, digital controllers, and on and off control devices. Let's first look at analog controllers, such as bellows-type pneumatic PID controllers, backpack-type regulating recorders, early pneumatic recorders, and electric PID regulators. Digital controllers include K&M single-loop regulators, programmable logic controllers, and Honeywell's DCS. On and off control devices such as counters, time relays, and controllers from Foxborough and Rosemount. That concludes this lesson. Thank you for listening. See you next time.